Welcome to matrix operations, where we perform arithmetic on matrices. Starting with the basics, a matrix is an array that can organize numbers. But arithmetic with matrices can be very different. We must start with being able to describe a matrix and its elements. So here's a matrix, and it is arranged in what we call rows, which are horizontal, and columns, which are vertical. The entries, or elements of the matrix, can be referred to by a number. So if I want the second row, third column, I would specify it by first the number for the row, and second the number for the column. So this is row 1, 2, and column 1, 2, 3. So this is the first row's second column, and so on. We also talk about the size of a matrix, and the size of the matrix is also specified row first, column second. So this is a 2 by 3 matrix, 2 rows, 3 columns. If you're entering this into a calculator, first it has to know the size of the matrix you're entering, and it gives you 2 little blanks. You must enter the row first and the column second. Matrix addition, and for subtraction, add the additive inverses of numbers. So 2 matrices can be added if and only if the same number of rows and same number of columns exist for both, and elements in corresponding position, add elements in corresponding positions. If you want to say subtract, it's okay. Mathematics is built on 2 operators, addition and multiplication. Subtraction is defined as adding the additive inverse, or the number we would add to get to 0, and multiplication is multiplied by the multiplicative inverse, or the number we would multiply by to get to 1. So here's an example. I have a 2 by 3 matrix with various numbers, and another 2 by 3 matrix with various numbers, and an addition sign. And we're going to say this equals. Now, how do we do this? Take the first row, first column, 2 plus 1, which is 3. Take the first row, second column, 0 plus negative 1. It's negative 1. And finally, filling out the first row, 6 plus 4. 6 plus 4 is 10. Second row, 1 plus 7 is 8. 2 plus 2 equals 4. And negative 3 plus 5 equals 2. So it's very simple. If you can add numbers, you can add matrices. It's just that you will have to perform the operation as many times as there are positions that are filled in the matrix. The number of rows times the number of columns. Here we try to add these 2 matrices. The first row has 2 positions here and 3 here. Well, what would you do with the 6 out here? They don't fit. If they don't fit, they cannot be added. So Addition isn't defined for every pair of matrices. This addition cannot be uh, done. These cannot be added. A 3 by 2 matrix can only be added to another 3 by 2 matrix. A 2 by 4 matrix can only be added to another uh, like size matrix, and so on. Now, multiplication by a scalar. When a scalar, perhaps as simple as a constant, multiplies a matrix, it multiplies each element of the matrix. So if I have 3 times a matrix, 2, 3, 5, 4, I would multiply the 3 by each position, each element. 2 times 3 is 6. 3 times 3 is 9. 3 times 5 is 15. And 3 times 4 is 12. So again, it's a very simple operation. And so you should not fear working with matrices. Well, then the question comes up, what if I have a matrix times a matrix? Not all matrices can be multiplied by each other. If matrix A is an A by B matrix with A rows and B columns, and matrix B is a C by D matrix with C rows and D columns, AB is possible if and only if B equals C. So they have to fit together just right. And the product is, and if the product is possible, the product matrix will be an A by D matrix. Matrix multiplication is not commutative. Commutative numbers, 2 times 5 is the same as 5 times 2. Matrix A times B is not the same as matrix B times A. That just doesn't work. The method of finding a product, AB, is to multiply each row of A by each column of B, pairing the elements and adding the products of each pair of elements. Now, what does that mean? I'll show you that with an example. The row of the left matrix being used and the column of the right matrix being used will determine the element of the product obtained. So, yeah, follow the example because that's the best way of seeing this. So here we have a matrix, 2 rows, 3 columns, and we can multiply by a matrix, 3 rows, 2 columns. So since a number of columns of the first matrix matches the number of columns of the second matrix, the number of rows of the second matrix, the product is possible. And the size of the matrix will be the number of rows of the first matrix and the number of columns in the second matrix. So we're going to get a 2 by 2 out. So let's take the first row and impact it on the first column. 3 times 1 plus 2 times 7 plus 8 times 2 times 6. So we multiply an element from the first matrix and an element of the second matrix. So in the first position, we multiply by the first position. The second position multiplies by the second position, the third position by the third position. So we would go through the first row, second column, 3 times 2 plus 2 times 4 plus 8 times 2. Then we take the second row and we do likewise. We impact it on the first column, 5 times 1 plus 6 times 7 plus 1 times 6. And then we finally finish with the second row, second column, 5 times 2 plus 6 times 4 plus 1 times 2. And then we do the arithmetic of what's there. And this final matrix that we would get is 65, 30, 53, 36. And the order of the matrices, if the order of the matrices is reversed, not only will we get a different matrix, but yes, the 2's would match instead of the 3's, and the size of the product matrix would be a 3 by 3. The identity matrix. Well, with matrices, we have a family of identities, depending upon the size we need. And the way they look, they're going to be a matrix. It's always going to be what we call a square matrix, where the number of rows equals the number of columns. There'll be ones down the main diagonal and zeros everywhere else. So the 2 by 2 identity matrix looks like this, 1, 0, 0, 1. This is the 3 by 3 identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. And if we multiply, if the multiplication is possible, the matrix A times the identity matrix I gives us back A. And the matrix I times a matrix A also gives us back A. So this is the identity matrix. We'll multiply with it and nothing happens to our matrix. Two matrices are inverses of each other if and only if A times A inverse equals A inverse times A equals the appropriate identity matrix, the one of the right size. Only square matrices are candidate to have inverses, and not all square matrices do. To find an inverse of a matrix, augment the matrix with the appropriate identity matrix. Then operate until the identity matrix is augmented with the inverse matrix. If you're familiar with reduced row echelon form in taking a matrix and solving a system of equations, we augment with the constants from the various equations. Here we augment with an identity matrix. So we're going to look for an inverse matrix 2, 1, 1, 3 to that particular matrix. And so we augment it with the identity matrix. The matrix then can be operated on, and what we can do is multiply, or we can take a product of one row and add it to another. And what we're going to try to get is the identity matrix here, 1, 0, 0, 1. It's not always going to happen. If it doesn't happen, there will be no inverse matrix. Not every matrix has one, even every square matrix. So your allowable operations include multiplying an entire row by a constant, and then adding or subtracting a multiple of one row to another row. Work on a pivot point entry on a diagonal from left to right, and then work to get zeros in the rest of the column. The problem is if you don't follow that order, you may end up messing up things that look finished. So in trying to get a 1 here, uh, that's one thing. Trying to get a 0 here and messing up the 1 is another. With 2 by 2s, it's not too bad. With 3 by 3s, working from too far down would be a problem. So we're going to take our original matrix and multiply the top row by 1/2. And these are the values we get. If you recall, the matrix was 2, 1, 1, 0. So we end up with 1, 1/2, 1/2, 0. And in teaching the matrices to college students, I can tell you right about now, students are screaming about fractions. If you're in college, your professor really thinks you know fractions, and if you don't, you need to figure out what you missed, because that is not the point of a course at this level. So next, we're going to add a -1 times row 1 to row 2 to get the 0 here. So -1 plus 1 is 0. -1/2 plus 3 is 5/2. -1/2 plus 0 is -1/2. And negative 0 plus 1 is still 1. Now we're going to go to the next pivot point right here. We want to get this to be a 1. So we're going to multiply by 2/5. So we don't want to mess anything up here. This row is going to stay the same in this operation. So 2/5 of 0 is 0. 2/5 of 5/2 is 1. 2/5 of -1/2 is -1/5. And 2/5 of 1 is 2/5. The next thing we would do is add -1/2 times row 2 to row 1. So we're going to try to get the 0 here. We got to take care of this 1/2. Well, -1/2 of 0 is still 0, so we don't mess anything up if we go in the right order. -1/2 of 1 plus 1/2 is 0. -1/2 of -1/5, we're going to end up with 3/5. So -1/2 times -1/5 is 1/10. 1/10 plus 1/2 is 6/10 or 3/5. -1/2 of 2/5 is -1/5, and we add that to 0, we get -1/5. This is our inverse matrix right here. And there is no division in matrix operations. Finding a multiplicative inverse and multiplying by it is the best we can hope for. So our inverse matrix, these two matrices are inverses of each other. The one we found and the one we started with. So we have an inverse pair. It's possible when we try to find the inverse matrix to get a row with a 0 and a pivot point. There's no way you're going to get a 1 in that pivot point without having it maybe transfer itself to somewhere else. You're always going to end up with a 0. Once you get a 0 in a pivot point, you're always going to have a 0 in a pivot point. And you won't be able to get the identity matrix out here. So in such cases, there is no such thing as an inverse matrix. And some of them look very simple and normal. Just because the matrix exists does not mean it has an inverse. Thank you, and I hope you will subscribe to the channel. Now, we have many other math videos in various branches of math. Uh, this one is in what is called uh, linear algebra. It could be tacked on to a regular algebra course, depending upon how advanced your course is. Certainly, if you don't see it in algebra, a linear algebra course would pick it up. Usually it's sort of included somewhere where one needs it. Well, thank you.